So, hello everyone. Welcome to our webinar, The Power of a Micropump, a big idea in a small package. My name is Stefan Tietze and I'm part of the business development team at Fraunhofer IPMS and will be the moderator for today. At the IPMS, we are focusing in our research activities on photonic microsystems, which includes micromirrors, micromirror arrays, as well as microactuators. And in the last years, we developed a completely new design approach of microactuation, which is called the Nano E-Drive. Besides possible application fields of microspeaker and ultrasonic transducing, the new approach ended up in an NED-driven micropump. So I'm happy to have the opportunity to introduce the group leader of the NED micropump, Dr. Christine Ruffert. Christine studied physics with main focus on optics at the Leibniz University in Hanover. Afterwards, she was responsible for research and education in the area of microproduction technology for at least 12 years. 2017, Christine came back to the roots of physics and started her research at Fraunhofer IPMS. Now she is responsible as group leader for monolithic integrated actor and sensor systems at Fraunhofer IPMS at the site location in Cottbus. Now some short facts about the course. In total, the webinar will approximately run for 30 to 40 minutes. And afterwards, we will answer the question you can ask by using the chat function. Additionally, the slides of the presentation will send out to all of you in the next days. So I want to take it short and have the pleasure to hand over the voice to Dr. Christine Ruffert. Welcome, Christine. Christine, you are still in mute. Now, welcome, Christine.
Okay, so hello everybody. I hope you can hear me well, and thank you, Stefan, for the nice introduction. Today, I would like to invite you to accompany me on a journey to the micro world, especially to micropumps. So the intention of the webinar is to show you how powerful even a very small micropump can be.
Christine, you are mute again.
Now it should be fine.
Yeah.
Can you hear me? Yeah? Okay, so I start all over again. So I want to introduce you to the institute structure and our business unit. Stefan already mentioned our business unit, which is called Monolithically Integrated Actuator and Sensor Systems, abbreviated MAS, and of course, monolithically integrated on silicon, as you might already know. And I want to present you some service and offers we have in our facility. So. Next, I would like to introduce you to in the nanoscopic electrostatic drive material, as already also mentioned by Stefan. And the abbreviation for this is NED, which is really nice because net is nice in German. I hope you will also like this nice approach. And I will present to you the actuator technology and some fabrication and characterization results. Then I will focus on the micropump because NED is the basic technology and the main idea to realize a micropump like we did. And I will show you the actuation principle, give you some idea of specific features, competitive advantages, and finally end up with some very fresh test results from the lab, from our PhD student. I will end up my talk with an outlook. We are also fabricating micro valves based on the net principle. And finally, I will give you a conclusion of my talk. So let's start with the institute structure and overview. Our institute is guided by two directors. One is Professor Lackner and the other one is Professor Schenk, and they are managing the institute in a collaboration. And the technical part, I hope you can see my mouse. Can you see my mouse? Yeah, so the technical part is on the right side. Start with the Center of Nanoelectronic Technologies, CNT, and their business, daily business is IoT, Internet of Things, and also next generation computing. And beside that, we have a business unit called WMS, Wireless Microsystems. Another one is called SLM, Special Light Modulators. Then we have AMS, Active Micro-Optical Components and Systems, and there's, this is about scanning micromirrors. And we have environmental sensing with us. And finally, our group, which is called, as I already said, Monolithically Integrated Actuator and Sensor Systems, MAS. And it should be remarkable that the branch, ISS, you might see it on the top, Integrated Silicon Systems, is located in Cottbus. Even of the main mother institute is found in Dresden, and the branch ISS is found in Cottbus, and part of the environmental sensing department is also located in Cottbus. So we are a growing group here in the area of Cottbus. And we all are supported by the engineering department, who are planning and greatly supporting us with the clean room fabrication. And the fabrication is finally done by the fabrication department on 200 millimeter MEMS wafers. And we have a small group also located in Erfurt, at the location Erfurt, in the project center Microelectronic and Optical Systems for Biomedicine, MEOS. This is in cooperation with 2 other Fraunhofer institutes. And the technical part is only possible with a really great administration department we can see on the left-hand side. So we have great support by administration, HRD, business development, who set up this nice webinar sequence or had the idea to present or to offer you with this webinar today. And then we have a quality and test section, and finally IT, who are enabling us to do this webinar today. So thanks to them at this point in time. And now I step into our technical part. NED, I already said, nanoscopic electrostatic device, and this is here in the center, and everything is about this NED actuator technology. So what can we do with this NED technology? We can move our position platforms in X, Y, and next year maybe also in Z direction. And we can realize ultrasonic transducers and towards hands-free gesture recognition. This is one of our purposes. Today we will talk about micropumps. So I put it in the center on the top. And another area of research, or already not even research, but industry standard, or silicon speakers. So we are building micro loudspeakers and aiming at the Internet of Voice, or enabling some specific things in the Internet of Voice. And microvalves will also be part of my today's talk, but very briefly. There are some projects in preparation. I want to mention them today. One is fiber scanners for medical applications, endoscopy, for example. Then we are caring about optical modulators, varactors, and tuning. And so maybe you have an idea how broad the application field of this NED actuator technology actually is. So maybe just a few words about our business unit. So as I said, we were in Cottbus, and half of the group is in Dresden, and we have some people working in Erfurt also. So we have 17 research members and about 10 students working for us today. We have laboratories for MEMS actuator characterization, for fluidic characterization, also acoustics. Our clean room access is twofold. One is the MEMS clean room, and the other one is at the CNT, the CMOS clean room I will show you in a minute. And we also have access to the research fab, Microelectronic FMD in Germany, which is the Forschungsfabrik Mikroelektronik Deutschland in German. And so you see, we are located in 4 federal states. We have Berlin on top, the FMD. We have Cottbus, our branch here. This is Brandenburg. Dresden is located in Saxony, our mother institute, and the project center MEOS is in Thuringia. So we are covering 4 federal states of Germany. So as promised, we have two clean room exercises. One shown on the left is the MOEMS and MEMS clean room. I think everyone of you knows the abbreviation, which stands for micro-optical electronic micro microelectromechanical system, and this is an additional combined with optics. And the area is 1,500 square meters, clean room class 10, which is quite good. And here we are processing 8-inch wafers. So we have 8-inch wafer line here, and the work is done in a 3-shift system. It is worth to mention that we are certified by ISO 9001 2015, and this is also including the location in Cottbus. And we have access to the CMOS clean room at the CNT. They are working with 300 millimeter corresponding to 12-inch wafers. And there are many tools for processing and so on, metrology, patterning. And here it is worth to mention that they are doing sub-nanometer characterization and a full process flow up to 28 nanometer technology and even beyond. So just to give you an impression, who are we, what are we doing? And we offer feasibility studies, system process development, prototypes, demonstrators, characterization and tests, and so on, foundry services, and we are glad to fulfill your needs. Now I come to the actual topic, MEMS, microelectromechanical systems. How do MEMS move? How can I move such a small system? One approach is taking a piezoelectrical material like PZT and making use of the piezoelectric effect. Another approach is the electromagnetic one. I take a coil, as shown here in the design, and a permanent magnet provide a strong DC field, and I can even combine the coil, which is not indicated in the picture, but sometimes I can combine it with soft magnetic material to guide the magnetic flux produced by the coil. And this is a good possibility, but normally the forces are very small because the forces are scaling with the volume, and in the micro world the volume is not so large. Another approach is taking shape memory alloys, for example, titanium, nickel, titanium, or nickel, titanium, copper, which are common materials. Next, we have thermal expansion. We can make use of thermal expansion to bend this cantilever here. And finally, we end up with the electrostatic approach. And I want to talk about that now more into detail. Electrostatic is a good candidate. Why? We have a low power consumption, as you will see later on. It is compatible with microtechnology processes. And the design implementation is quite easy. And let's have a look at the physics behind the electrostatic force scaling with the square of the applied voltage applied to the electrodes. And it is scaling with the inverse of the square of the distance between the electrodes. So this means the smaller the gap between the electrodes becomes, the higher is the force. And I can also enhance the force by an increase of the applied voltage. But normally we have a real problem with electrostatic forces. There's a phenomenon called pulled in. And what this means, I will show you in a second. So an electrostatic device is normally considered or can be set up as a capacitor, as we know from school. I think you can see on the left-hand side of this sheet. And when I apply a voltage, the upper electrode or the electrodes will approximate to each other. The upper electrode comes down in this case, and there are two forces competing. One is the electrostatic one I already mentioned just before, and the competing force is the restoring force from Hooke's law, which is proportional to the distance between the electrodes, proportional to d. This means when d becomes really small, the electrostatic force is increasing very much, and the restoring force cannot keep the electrode back, so the upper electrode will collapse, and this is what happens normally. Here's the circle of this configurations. When you start at a distance d0 and you apply a voltage written on the x-axis, then the upper electrode will bend down. In this example, will approximate the bottom electrode, and at a certain point, the electrostatic force will exceed the restoring force and the upper electrode will collapse. And this is indicated with a limit of stability in this design, and you can see it in the graph here, indicated by the red line. And then you have a pull-in, so the two electrodes will collapse, nothing happens anymore. And with a bit luck, you might cause a release when you go back with a voltage, but normally you have to take really mechanical forces to separate the electrodes from each other. So with our system, we don't have this problem, and I show you why. Consider a dome-shaped structure, like here on the left-hand side, like from a church, and we adapt this shape for the upper electrode, as you might see here in the sketch in the center. And so the top electrode is shaped like a dome or like a roof. And with this topography, I will explain what happens. The upper electrode will bend down, or will try to get into contact or to lower the distance to the bottom electrode. But this is not possible in this configuration. And what happens? The side walls on the left and right hand side here will tilt and cause a stretch here. Oh, sorry, that was not my intention. And will cause a tilt here. And imagine you take a couple of such LED cells and put them in a row, like indicated on the bottom. And when you apply a voltage and the upper roof will bend down and the side walls will tilt, what will happen? The cantilever will bend. And this is what we are making use of in our net actuator systems. I will show you in an animation. So we have an all-silicon system beside from the spacer, which is made of alumina in this case to insulate the upper from the bottom electrode. So we have all silicon here and on the top also. So in first systems, we also use titanium aluminide, but nowadays it's a full silicon system. And we define a neutral plane. We apply a voltage between upper and bottom electrode, and forces will be created and trying to bend the upper electrode down or nearer the bottom electrode. And what will happen, as I explained to you just a minute before, the cantilever will bend. And you can do the other way around. You can put the spacer instead in the valleys, you can put them on the top here, and you will create a force which is lifting the cantilever upwards. So with this system, we have no pull-in forces. We can create very large forces because we can create really small air gaps here up to only a few hundred nanometers, and we can achieve a very large deflection by using the cantilever effect. The system has a low power consumption, around 0.0 milliwatt. We have a scaling advantage, and the system is CMOS and ROS compatible. We have two possible configurations. We can create a lateral movement, which is in plane of the wafer of the substrate material. And alternatively, we can create an out-of-plane movement, which is shown on the right-hand side, called VNet for vertical movement. Those corresponding technologies are as follows. On the left-hand side, for the LNet, we are using bulk micromachining, which means the system is fabricated predominantly by deep reactive ion etching, which is also known as Bosch process, and this is for patterning silicon with very, very deep trenches. And both electrodes are made of silicon in this case, and the spacer are made of alumina, which is deposited by atomic layer deposition in the holes which have been created by deep reactive ion etching before. For the VNet, there are two alternatives possible. One is surface micromachining. In this case, the electrode gap is made by sacrificial layer edge. So we have a sacrificial layer in between the upper and bottom electrode. And in this case, top or even both electrodes are made by physical vapor deposition made of thin metal films. And the supporting electrode could also be made from silicon on insulator. Alternatively, we can use wafer bonding. So we take two wafers and create the gap by bonding of these two wafers. In this case, both electrodes are made of silicon and the spacers are made of thermal silica. So these are the main configurations, and we can of course combine them. So we have the out of plane movement, the in plane movement, so the VNet and the LNet as basic forms, and we can combine them to a 3D movement, which is shown on the right hand side on the top. And we can also think of complex forms like linear movement, and we can tilt mirrors to when we put the NED drive underneath. And we can also think of curved plates, for example, to create a membrane pump or whatever. So to give you an idea how the fabrication is carried out, starting from A, we take a silicon wafer with buried oxide, which is indicated by the purple line here. Then we do a wet chemical etch by KOH, and with an angle of 54.7 degree. And next, the alumina insulation is deposited here on the pattern surface. On the next step, C, the titanium, I already mentioned the first systems were made of titanium aluminide on the top and silicon on the bottom, or even both titanium aluminide. And the electrode material is deposited here. Next, the insulation, silica, is deposited in step D. And further on, we have another titanium aluminide layer. And in the next step F, we have a backside edge up to the oxide layer, which defines the cantilever thickness. And the next step, G, we define the rim, the outer shape of the cantilever. And finally, SiO2, so the silica is removed here to void the air gap and also to free the bottom part of the cantilever. And as you might see on the right hand side, there are two variants for the bottom electrode. So we can create, as I showed you on the left hand side, we can create a two electrode system as shown on the top, and we can bend it down and up. And the respective angle is defined as negative in this case and as positive in the case the system goes up. And we can also think of a system, or we realize a system which has a top electrode made of titanium aluminide on top, and the bottom electrode or mass is just silicon with alumina on top. So we fabricated the system in the clean room, and here you see a micrograph, a top view of such a system, of such an electrostatic bending actuator. You see the bottom and top electrode contacts on the right hand side. You see the trenches, and this is a type of a VNet, so a vertical bending actuator out of plane. And in addition to this micrograph, I would like to show you some SEM images from a scanning electron microscope. And you see on the top, on the left-hand side, a section of about a couple of 100 micrometers. And you see an enlargement on the right-hand side, and you might see the single layers. And on the bottom, they are indicated. So you see the top electrode, which has a thickness of 500 nanometer in this case. And this is made of titanium aluminide. And then you see the air gap, and the air gap is written on the left-hand side. This is about 200 nanometer in this design, so very small. And the bottom electrode is also made of titanium aluminide, in this case 400 nanometer. And then you see the electrical insulation, which is 400 nanometer alumina in this case. And you see the angle as defined before is negative in this way because the VNet groove is going down. And the section here is a couple of micrometers. So here's the verification of the system. You see another design I would also like to present to you that we fabricated various designs and investigated the systems very deeply. So here's a design with a very thin bottom electrode. In the design before we had a thick bottom electrode, and here we have a thin top and a thin bottom electrode with a thin air gap in between. In this design, it's about 1 micron. You might also recognize the spaces here, which are made of alumina in this case. The cantilever length of this design was 2 millimeter. And you see here for verification, validation of the system at 60 volt, the ulnar tip has a deflection of 89 microns, was one of the first verification investigations. And in the graph in the center here on the bottom, you see the absolute cantilever tip deflection given in micrometer, and also the absolute curvature. Where's my mouse? The absolute curvature of the cantilever here, and both dependent on the control voltage with this, which ranges from about -50 to +50 volts in this investigation. So with this nice concept of an NED, nanoscopic electrostatic drive, we can set up a manifold of microcomponents such as resonators, sensors, acceleration sensors, mirrors, translation mirrors, and so on, optical switches, linear actuators used for micro positioning, pumps, valves, so microfluidic systems, and the speakers, ultrasound, micro loudspeakers. Based on these micro components, we can set up a lot of target applications. For example, sensors can be used for material analysis, the mirrors for optical coherence tomography and microscopy, of course, and for FTIR spectrometers, and the linear actuators for bright displays. And I will skip this for a second. The micro loudspeakers can be used for hearing aids, hearer bells, distance measurements, and so on. And this is also where the arrow is here. That's already done. And what I want to focus today, as promised, is micropumps and also microvalves, which can be used for microfluidics, cooling technologies, and some other nice applications. So let's have a deeper look into micropumps. What is the state of the art? So there are a couple of micropumps on the market, for example, from Schwarzer Precision, eccentric diaphragm pumps from IVEC, displacement pumps here shown in the center. And I think the pioneer was Bartel Mikrotechnik, who created this nice pump shown here, which is based on a piezo membrane. And typical applications for micropumps are medical technology, gas analysis, monitoring, patient monitoring, point of care applications, and so on. But I think those pumps who are in the area of some centimeters even are not suited for small space or even in body applications. And I wouldn't like to have such a pump in my body actually. So we thought about creating a real micropump that can be maybe implemented even in the human body. And so how to do with this? Based on the NED principle. We take four of the NED cells. Yeah, the cells I showed you at the beginning of my talk. We take 4 of the cells and put them in a row, shown here on the right-hand side. And then when you apply a voltage, you will achieve a banding of this double S configuration. And now you can see why it's called double S. You have an S here up to the center and another S here. And then you take 2 of those double S patterns, you might have a structure like this, shown in this animation on the bottom. And when you put some valves here at the in and outlet of the part, and you excite the system, you might create a pumping effect. I think this should be clearly visible in this nice animation. And what happens when you excite the voltage and you create a bending of the cantilever, you create a bending movement, of course, of the cantilever here, and you create a stroke, or this results in a stroke volume between the two, or NED arrangements, let's call it like that. So I hope this is clear up to this point in time. And what features does the NED-based micropump have? It is designed for gases and liquids, and they can fulfill customized needs. For example, when you have special wishes or concerns for footprint and fluid design, we can design the NED-based pump up to a certain value, of course, and provide you with this pressure and flow rate you need. So there are some examples for designs for liquid and also for gases given here on the left-hand side. And I want to show you the standard force displacement curve also. So it looks like this, yeah, and this is the load curve of a spring. And when this goes up, or when the slope is too high, the blocking force is even too high, and you have rather a very small displacement. And the other way around, when it goes here, the load force of the spring, which is the cantilever in this case, you have a small blocking force and a large displacement, but the pump force is also low. So this is not desired, and this is the ideal case, and our pump is following this. So what does the pump look like in a cross section? You see a cross sectional view here, and of course we have clearance leakage because the single beams, NED or cantilevers, cannot be attached to the top and bottom, otherwise they wouldn't be able to move. So we have small clearances here, and we investigated the dynamics or the change of dynamics due to clearances. So this is a simulation result. You see the maximal deflection depending on the time. And you see that with clearances you have a much higher dynamic in the system. But of course, the pumping rate is smaller because liquid or air is passing through the neighbor chambers. So stacking is very useful to increase the stroke volume, to increase the pressure difference the pump can supply. And here I have an example for you. So as medium, we chose air and a dielectric liquid called Novec 1700. And we stacked our system up to a size of 0.0 millimeter times 2.4 millimeters times 0.9 millimeters. And for air, we applied an actuating voltage of 300 volts. And we are achieving an operation pressure difference for the pump of 5 kilopascal or up to 5 kilopascal, and the flow rate is about 150 microliter per minute. For the dielectric, we investigated corresponding to the applied voltage of 140 volts. We have an operation pressure difference of 7.5 kilopascal, and the corresponding flow rate is 20 milliliter per minute. We will also see this later in a graph I will show you as a laboratory result. So thanks to Bartels and other pioneers performing such great work and doing some basic research and creating a market for micropumps, we are able to provide such customized micropumps as I said, or as I offered or I'm offering to you today. And I made a small competitive table between our net vamp pump and the piezo membrane pump from Bartels, which was I think the first one on the market, the first micro pump, very famous. And we are pumping liquids and gases, as I already said, and the applications for liquids are, for example, industrial confined environment, CPU cooling, medical applications. And for the back pressure, I can give you the value 0.07 bar, and the flow rate is about 0.02 SCCM. And for the gas, we are just about to characterize, currently, we are characterizing gas pumping in our laboratory. So I can give you, surely I can give you later some values when we get in touch after the webinar and if you're interested in gas pumping. So the adaptation of the working point is excellent with our pump. The production scaling is also very good. As I already said, power consumption is very small. and the size, of course, also. And because one stripe is very small, so one chip is in this case 2 millimeter in length because of the cantilever length, and 1 millimeter wide, and the thickness is also 1 millimeter. So the size and miniaturization is very promising, and the integration is, as a consequence, the integration is high or even very high. Here are some results from the lab, as I promised to show you later on. I told you at 140 volts we have 20 microliter per minute. So you see at 131 volts we have about 18 microliters. So this is corresponding. And we see the flow rate dependent on the actuation frequency in hertz, on a logarithmic scale for 3 values of applied voltage. And we see as the flow rate increases with the applied voltage, and this is done for the dielectric liquid Novec we use for our investigations on liquid pumping in the lab. And I will come back to this peak here, which is at 1.5 kilohertz on the next slide. But before, I would like to show you the principle of actuation here. So we have a real system. The scale is 50 micron, and the liquid is normally passing here and then coming back here and here and here, like a meander. And of course, we cannot pump liquid here because in case we would like to pump liquid, we would have to put a cover on, and then we cannot see anything anymore because there's a silicon wafer on top. And so we just would like to show you the principle of actuation without cover, and of course without liquid and without the ability to create a pressure in this chambers. So you see the cantilevers moving, and for the pump, as I said, we have to put a cover on top to create a pressure in the chamber. So there are some further measurement curves from the lab I want to share with you. We have the flow rate in microliter per minute dependent on the back pressure on millibar given on the left-hand side, and this is for the peak at 1.5 kilohertz. We saw at the slide before, also for 3 voltage values. And on the right-hand side, you see the fluidic power given in microwatts, depending on the back pressure on millibar, also the 3 curves for the 3 voltage values. And we see the maximal fluidic power measured in the lab with our micropump at 0.22 microwatts at an exciting voltage of 131 volts and 30 millibar back pressure. Here we see a macro demonstrator just to show you that the principle of a piezo, in this case we have a piezo bending cantilever here. I will just start the video and then I will explain. So we have the piezo bending actuator here. The system is about 10 centimeter times 5 centimeter or so. And we have some particles here as tracers, so you see how the liquid is moving. And we have some valves here and here and here. I started again. They are passive in-plane polyethylene valves, and as test medium, sunflower oil with added tracer particles is used in this case. So to summarize what I presented to you, there are many applications for our micropumps ranging from lab-on-chip systems, point-of-care medication, drug delivery, and some more in this field, medical, pharmaceutical industry. I think cooling purposes are a good idea, also IC cooling, CPU cooling, GPU cooling, and we are thinking of embedded lubrication to make use of the pump for lubrication applications. There are many unique selling points I want to point out at this point at my presentation. The pump is really small, as you saw, so we have small size, we have a low energy consumption, 0.1 milliwatt. We have a precision of the fluid volume, dispensed with a pulse-free flow, which is really worth to mention because normally micropumps are featuring a pulse, ongoing a pulse, and this is not the case with our pump. We are applying a monolithic batch process. This means we are fabricating many pumps in the same fabrication process, or the same process flow. And we can provide customized flow rates and create pressure ratios following your needs. And also the size tolerance of particles, if you would like to pump particles, is quite large. The system is compatible with CMOS and ROS, and the pump features a small, or only needs small space. The integration is very high. So we are also working on we are working on micro valves. There are two concepts, and the status is that the systems are currently fabricated in the clean room, and we expect them to come out of the clean room during springtime next year, and then we are able to characterize the system. So there are two approaches. One is the shutter valve on the top, serving for flow regulation, and this way that the net actuators shown in red here on the left, in the left part of the picture, will contract and pull this part here to close the hole, which prevents the liquid or air to go through from top to the bottom. So this is the direction of flow as indicated by the arrows. And we have a small fluidic resistance with the system, which is smaller than about 1 liter per minute at a pressure of 2.5 bar. And the bottom system shows a plunger valve. And in this case, we have the net actuators on the left and right hand side of this plunger. And when they are actuated, they push the plunger to close the hole here and to prevent the liquid to pass from top to the bottom. So this is rather a flow control valve and an on-off valve, which can be used for liquids as well as for gases. We're thinking of many application fields of our net microfluidic devices, so medicine, biopharmacy, various fields in the industry, lubrication, as I already said, conditioning systems, IC cooling, electronics, and so I think our Nano eDrive has a big future. And I thank you for your attention. Just to summarize, I put some of the unique selling points on the final sheet, and it's my honor and pleasure to announce the upcoming webinar, which will be on the 13th of January next year. My colleague Monika Beck will talk about Li-Fi communication at the speed of light. Now I would really like to thank you for your attention. I would be pleased to answer your questions. Thank you.
Thank you very much, Christine, for this really interesting introduction into the system, the technology, and also into the applications. Dear viewer, if you have some questions, it's now time to use the chat function.
So I mean, yeah. If you don't have questions at this point in time, I think the sheets will be provided, and you have my email address, and you can get in touch with me personally.
That was the thing what I also would like to say.
Yeah.
So finally, thank you very much for joining our session today, and I hope to welcome you to our next webinar session with Monika Beck in the new year. Until then, I think we wish you a very Merry Christmas and a Happy New Year, and have a nice day, I would say. Bye-bye.
Bye.